The general title for this lecture is The Existence and the Proof by Contradiction. But we need first to show the difference between how to prove and how to disprove. First, I'd like to provide an important point regarding the quantified statements. If I have a statement like this one, there exists X belongs to some set, let's call it R, P of X. Here, this P of X is depending on this X. And now we need to negate this statement. So the negation of this statement, negate of there exists X belongs to R on condition P of X, this equivalent to the negation of there exists is for every X belongs to R on condition the negation of P of X itself. What if we have statement for all X belongs to R, P of X? The negation of for every statement is equivalent to the negation of for every, just to provide an example, by there exists X belongs to R on condition that the negation of P of X. So based on these points, we need to show the difference between how to prove and how to disprove. We know before how to prove, and what about the techniques of proofs? Okay, but regarding the disprove, in mathematics, we sometimes need to prove that in something does not exist, or in something is not possible, or in something is wrong. For the proof, on the short run, we have two types of statements to prove. For every and there exists. To prove for every, so you have to provide a full proof using any of the four techniques that we covered before: direct, contrapositive, vacuous, and trivial technique to prove a statement with there exists. So just to provide an example. While for the disprove, we have two types of statements. Disprove statement with there exists, disprove a statement for all. To disprove a statement with there exists, so just to provide a proof, there exists, its negation. So for every, which is just a proof, provide a proof. But regarding for every, here we have two ways to disprove a statement that's starting with for every. The first way is to prove the negation, negate the statement, and then prove this negation. The second way for disproving a statement that's starting with for every is there exists counter example. Just to provide a counter example. So now in example 1, consider the statement. Have x belongs to set of real numbers, then x squared minus 1 to the power 2 is greater than 0. Show that the above statement is false by showing up a counter example. We are looking for here a counter example for this statement, which means that we are looking for x squared minus 1 to the power 2 not greater than 0. It may be equal x squared minus 1 to the power 2 equal to 0, or x squared minus 1 to the power 2 less than 0. This is not possible. In the set of real numbers, this is not possible. But maybe we find the value for x that's satisfying this form, x squared minus 1 to the power 2 equal to 0. Actually, this is satisfying for x equals to 1. So for x equals to 1, we get that in x squared minus 1 to the power 2, replace x by 1, you will get 1 power 2, for sure it's 1, 1 minus 1 to the power 2, this equal to 0. Then x equal 1 is the counter example for this statement. Then x is the counter example for this statement. So the point here, or the clue here, is negate this statement. If x belongs to R, the same as for every x belongs to set of real numbers. Then negate this statement. This is the point here. In example 2, another statement to disprove. If x belongs to set of real numbers, then 10 squared plus 1 equals to 6 squared. From the first look to this equation, you will see that this is not possible to disprove this statement, as in already we are trusted with the truthness of this statement from calculus 1. But the wrong here with if x is a real number for every x belongs to R. Both statements together are wrong. How come? Actually, here we know that tan x is tan x the sine x divided by cosine x, which means that we will expect points for singularity for this function. What's the meaning points of singularity? Points or values of x that makes this cosine equal to 0. And we know that in mathematics, the division by 0 is not possible. So now we need to think about what are the values of x that makes this cosine equal to 0. If x equals to pi over 2, positive or negative. If x equals to 3 pi over 2, plus or minus 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So this means that in since tan, and the same for sec, the same case for sec, already we know that in sec x is 1 divided by cosine x. And we know that in tan and sec both are not defined at these values, plus or minus pi over 2, plus or minus 3 pi over 2, and so on. This means that in tan square plus 1 and sec square both have no numerical value at these values. Consequently, tan square plus 1 and sec square plus 1 are not equal at these points. So this means that x equals to pi over 2 negative or positive, 3 pi over 2 positive or negative, and the same for 5 pi over 2 positive or negative. These values are considered as counter examples for this statement. The same here in example 3. We would like to disprove this statement. If x belongs to a set of integer numbers, then x square plus x divided by x square minus x, this equals to x plus 1 divided by x minus 1. I think that is clear if we substitute x equal to 0. So the left hand side will lead to 0 divided 0, while the right hand side will be equals to 1 divided by negative 1, which is negative 1. So for x equal to 0, this equation is not satisfied, which means that in x equal to 0 is the counterexample for this statement. In example 4, it's requested to disprove the statement that for every positive odd integer, 3 divides n square minus 1. What's the meaning of 3? What's the meaning of this sign? It's 3 divides n square minus 1. This means that in n power 2 minus 1 is a multiple of 3, which means that in n square minus 1 can be written as 3 times another integer, 3 times k, where this k belongs to set of integers z. I think that it's easier to provide a counterexample. This counterexample must be odd to satisfy the first part of this statement. It must be odd, but at the same time, it has to negate the statement in 3 divides n square minus 1. Okay, now let's think about odd value that break this statement. At n equals to 1, we get that in n square minus 1 will be 1 minus 1, which is 0. So this 0 can be represented as 3 times 0. Which means that n equals to 1 does not disprove this statement. We are looking for a counterexample that's disproving this statement. What about n equals to 3 at n equals to 3? So we get n squared minus 1 will be 9 minus 1, which is 8. So this 8 can't be represented as 3 times k. Okay, so this means that in n equals to 3 is a counterexample for this statement. In example 5, disprove the statement if n is odd, then n squared minus n is odd too. So this means that in here we are looking for an odd integer that satisfies that in n squared minus n not odd. We need to disprove, not to confirm this statement. We need to disprove this statement. So we are looking for a value of odd integer for n that makes n squared minus 1 is even at n equals to 3. So at n equals to 3, we get that in n squared minus n, this will be 9 minus 3. 9 minus 3 is 6, which is even. So n equals to 3 is considered as it's a counter example. Now in example 6, disprove this statement. If n belongs to a set of integers in n, here we have if p then q. If p then q. So p here is in n squared plus 3n is even. Q here is in n is odd. We learned before that and we can deal with such type of statements. So we use the contrapositive technique by stating that in let n as it is, let n belongs to a set of integers. Then if n is even, then n square plus 3n is odd. The point is we need to disprove this statement. Okay, so to disprove this statement, just substitute with the value of n, which is even, and then I expect to get an n square plus 3n is even to say that in this assumed n is a counter example. Okay, so for n is even at n equals to 2, so we get that in n square plus 3n, this will be 4 plus 6, which is 10. This even value, so this means that in n equals to 2 is a counter example.